In this video, I will guide you through the configuration of BGP on the NOKIA 7750 service router. BGP stands for Border Gateway Protocol. BGP is the routing protocol of the internet, as it is the protocol that handles the global routing table. In this lab, we will duplicate the connectivity between PE1 and PE2 as in the previous lab, but we will use BGP instead of OSPF. We will configure CE1 and PE1 to be within ISP1, and PE2 will be within ISP2. Same as in the previous lab, CE1 has no direct reachability outside of ISP1, hence it must always pass through PE1. ISP1 and ISP2 are separate autonomous systems, therefore we will configure eBGP and the required policies to connect the two autonomous systems together and exchange routing information. I have broken the required configuration task into the following 7 different tasks. The first task is to remove OSPF on PE2, and on PE1 remove the interface going to PE2 from within our OSPF process. Second task is to configure the autonomous system IDs on CE1, PE1 and PE2. And the third task is to configure external BGP between PE1 and PE2. The fourth task says we have to configure an export policy on PE1 and PE2 to export directly connected subnets into BGP. The fifth task is to configure iBGP between PE1 and CE1, and the sixth task is to configure PE1 to send the next up self packets to CE1 for routes that were learned from inside ISP1. Last task we have to do is to modify the existing policy on PE1 to include all the routes learned from within the autonomous system. Let us now proceed with our task 1, which is the removal of OSPF on PE2 and the removal of the interface going to PE2 from our OSPF process on PE1. On PE1, we want to remove the interface going to PE2 from our OSPF process, so we issue the configure router OSPF. Our previous area was area 0. We issue the info here, and from here we want to shut down the interface going to PE2 and then remove it from our OSPF process. We issue the interface to underscore PE2, shut down, and then we issue the no interface to underscore PE2. It return info again to see what we've done. We can now see that that interface has been removed from our OSPF process on PE1. On PE2, we want to remove the OSPF process entirely. To do that, we go into configure router OSPF and area 0 info. We've only got one interface there. Exit out of that, and then configure router OSPF, shut down, configure router no OSPF, enter. To double check to confirm that we've removed OSPF completely from PE2, we issue the show router status command. This shows us the routing protocols that are currently configured, and from the output you can see that OSPF version 2 has been removed from the configuration of PE2, and on PE1 we should still have it there, but we issue the same command, show router status. We still have OSPF running, but we don't have the interface going to PE2 within our OSPF process. That has completed our first task. We now move on to the second task. Our second task is to configure the autonomous system IDs on CE1, PE1, and PE2. If we refer back to our network diagram, CE1 and PE1 are within ISP1 and they have the autonomous system ID of 65001, and PE2 on the other hand is within ISP2 and it has the autonomous system ID of 65002. Let's now go to the CLI and do that. So from the CLI of CE1, we issue the configure router command, it return an autonomous system. This has to be within 65001. It return exit all. That completes the configuration on CE1. We move on to PE1 and do the same thing. Configure router, it return autonomous system. It has to be the same as CE1, which is 65001. Enter, exit all. Lastly, we go on to PE2 and configure the same, but with a different autonomous system ID. So configure router, enter, autonomous system. This will be 65002. Hit return, exit all. That completes our task 2. We now move on to task 3. Our task 3 says we need to configure external BGP between PE1 and PE2. Let's go on to the CLI and do that. Before we proceed, let's have a look at the routing table on PE2. We issue the show router route table. PE2 only has local networks within its routing table. These are the locally connected interfaces on PE2. Let's issue the same command on PE1. Actually, I have already done that. You can see that PE1 on the other hand has more routes within its routing table. This is because PE1 is running OSPF with CE1 and it's also got the local interfaces within the routing table. So let's start off from PE1 with our configuration of external BGP, and to do that we issue the configure router, enter, BGP, enter. We need to create a BGP group. Let's call our group external underscore BGP. It return. Our pair is, our neighbor is PE2. The PE2 interface IP address is 140.10.0.98. Let's verify that and be sure. We go to our network diagram. PE2 far end IP address interface is 98 and PE1 has got the 97. So let's carry on with our configuration. It return there. Our pair AS will be the AS of PE2, which is 65002. It return exit, info to see what we've just configured. We have configured a BGP group called external BGP with a neighbor IP address of 140.10.0.98 and a pair AS of 65002, which all corresponds with the information we have on our PE2. We now need to go to PE2 and do the same thing towards PE1. So on PE2, again, we issue the configure router, enter, BGP, and configure router, BGP, enter, group. We call this same as we did on PE1, external underscore BGP. This doesn't have to match, by the way. It's local to the routers. It does not have to match. So enter. Our neighbor is PE1, which is on 140.10.0.97, and the pair AS of PE1 is 65001. Enter, exit, info here to see what we've done. We have a neighbor of 140.10.0.97 and we have a pair AS of 65001. That looks good to me. and it's not shut down. Exit all. Let's now check to make sure both PE1 and PE2 are seeing each other as BGP pairs. And to do that, we issue the show router BGP neighbor. If you tab, it will tell you what neighbor you have. So on PE1, we have the neighbor of 140.10.0.98. It return. As you can see, the state is established, and we need to see the same thing on PE2. So show router BGP neighbor. Our neighbor IP address is 140.10.0.97, which is PE1. Hit return, and what you want to see here is the state has established. Quit out of that. Before we go, let's confirm if those two routers are sending any routing updates to each other as of yet. So to do that, we issue the show router BGP neighbor. Again, our neighbor from PE1 is PE2, 140.10.0.98. Advertise routes. Are we advertising anything, any routing updates from PE1 towards PE2? Hit return, and as you can see, we're not doing anything. We're not sending any routing updates from PE1 to PE2. Let's go over to PE2 and do the same thing. Show router BGP neighbor. Our neighbor is 140.10.0.97. Advertise routes. Likewise, PE2 is not sending any routing updates to PE1. That has confirmed that we have BGP neighborship between PE1 and PE2, but we are not sending any routing updates. This has completed our task 3. Our task 4 says we have to configure an export policy to export directly connected subnets into BGP. Let's go over to the CLI and do that. If you remember, in the previous exercise, we configured an export policy for OSPF. Let's view what that export policy says. And to do that, we issue the show router policy, and it's called the distribute loopback. Hit return. So what this is saying is the first entry and the only entry for now is saying from the protocol direct, which means anything that is directly connected, accept it. We have the same exact policy on PE2. Let's confirm. Show router policy, distribute loopback. The same thing. So we're going to use this exact policy. If we had not got this in place, we will have needed to create one. But because you saw me create one with our OSPF exercise, there's no need to repeat that task here. If you missed that, please go back to the previous video and check how we did that. So let's carry on with our task 4, which says we need to use this same policy or a new one within BGP to export directly connected networks. So we go into configure router, return BGP. Here we want to use the export command, and then we want to set our export policy as a distribute, our existing distribute loopback export policy. Return there, exit all. We do the same thing on PE2. Configure router, return BGP, export, and our distribute policy. Exit all. Before we complete this task 4, let's now again check and confirm what both PEs are doing in terms of advertising routes to each other. So we issue the same command as we did earlier, which is the show router BGP neighbor, and our neighbor from PE1 to PE2 is the 140.10.0.98 advertise routes. Are we now advertising any routes towards our neighbor PE2? Hit return, and as you can see, yes, we are. So the policy is now telling BGP that you can advertise all your locally connected networks towards your pair, which is PE2. Let's double check and see what PE2 is sending back towards PE1. With the same command, show router BGP enable. Our enable is 140.10.0.97. What are we advertising? It return. Likewise, PE2 is now also sending its locally connected networks towards PE1. That has completed our task 4. We now move on to our task 5. Our task 5 is to configure iBGP between PE1 and CE1. Let's go over to the CLI and do that. So from PE1, we need to now configure iBGP towards CE1. And to do that, we issue the similar command that we did before, which is the configure router, return BGP, return. This time around, we're going to create a different group, and we're going to call it internal underscore BGP. Return. Our neighbor IP address is the system IP address of our CE1. This is one of the major differences between eBGP and iBGP. iBGP connects using the system IP address. This is the reason we need a routing protocol, an interior gateway routing protocol, which can resolve that system IP over within the autonomous system. So this is why we left the OSPF neighborship between PE1 and CE1 in place. That's why we left it in place. We did not take it out because we need it to resolve the system IPs, the system interface IP addresses of PE1 and CE1. So let's carry on. So our neighbor is the CE1, which is 140.10.0.12. And the pair AS will be the same as with PE1, which is 65001. Enter, exit, info. Now we've got two groups. The first group is the external BGP that we did previously, and the new group that we just configured now is the internal BGP, which is going towards our CE1. Let's now go over to CE1 and complete that task. So again, here we issue the configure router, return BGP, return. We create the group. We call it internal underscore BGP. Again, the name does not need to match. They are locally significant. It return. Our pair AS is the same as PE1, 65001. Return, and our neighbor is the system interface IP of PE1, which is the 140.10.0.1. Enter, exit. If we issue the info command here, we'll see what we've just configured. So on CE1, we have configured a group called internal BGP with the pair AS of 65001, and the neighbor is PE1. It's on short as well, so it's active. So on PE1 as well, we've done the reverse back to CE1. Let's now check the neighbor relationship between PE1 and CE1. And to do that, we issue the show router BGP neighbor. This time around, we want the system IP of PE1. Again, as you can see, the state is established. That's all we're concerned about for now. We now go back to PE1 and issue the same. Show router BGP neighbor. This will show us two neighbors, but we know we want to check the neighbor status for CE1, which is the 140.10.0.12. Return. Again, it is established. Before we go over to the next task, I want to show you something that will be very beneficial to your understanding of how BGP operates between iBGP and eBGP. If we go back to our PE2, you can see that all the networks or subnets or routes, if you want, that are being sent towards PE1, they have the next up IP address of PE2's far end interface. Let's issue the same thing on PE1. What is PE1 sending to its new neighbor, its new iBGP neighbor of CE1? So we issue the show router BGP neighbor. This neighbor has to be CE1, which is 140.10.0.12 advertised routes. Hit return. So as you can see, PE1 is also sending the same prefixes that it received from PE2 directly to CE1, but it's not changed the next up IP address. So it's still using the far end IP address of PE2. The problem now is CE1 does not know how to get to that next up IP address. So we still have a problem, and I'll show you in our next task how to resolve that issue. Our next task, which is task 6, is to configure PE1 to send the next up self packets to CE1 for routes that it learns from outside the ISP1. This is the way we resolve the issue described previously, which was that PE1 was sending the external learned routes with the next up address of an interface that CE1 does not know how to get to. So if we look on CE1 as well and issue the show router BGP neighbor, which is the neighbor is PE1, what routes am I receiving from you? If you hit that button and see the output, you can see that yes, I'm receiving all this from you and it's got the right information as far as you're sending it to me, but I just don't know how to get to it. It's got the right AS, it's got, you know, everything it's learning the BGP routes, but it cannot reach it, as you can see. So the way we fix that is what our task 6 says we should do. Configure PE1 to send the next up self packets to CE1 for routes that it learns from outside the ISP1. So let's go ahead and do that. So on PE1, we'll issue the configure router, return BGP. We want the group internal, return. We want to now issue the next up self command here. Exit all. This might take a while to take effect. Issue the admin save. And now if we issue the same command as we did earlier, which was the show router BGP neighbor, the neighbor of CE1, which is 140.10.0.12 advertised routes. As you can now see, there's a big difference in the next up that PE1 is sending towards CE1. It's now saying to CE1 to get to the 150 network, send all the packets to me. I will do the routing for you. As opposed to what we were saying before, which was the 150 network can be reached on the 140.10.0.98 IP, which CE1 does not know how to get to. Now let's go over to CE1 and see what CE1 is now receiving from PE1. We issue the same command, which is the show router BGP neighbor 140.10.0.1, but what am I receiving from you this time? The received routes. Hit return, and again we can see a major difference in the next up IP address of all this subnets that was received from PE1 from PE2 in PE1 and then forwarded to CE1. So previously, before we did the change, we were receiving, CE1 was receiving that IP address, as the next stop for this 150 network. But after the change, it's now saying, for me to get to the 150, all I need to do is send it to PE1, which I know how to get to anyway. So before we leave, let's just have a look at the routing table. There's another thing I need to show you. If it's show router route table on CE1, remember we've got OSPF running in between CE1 and PE1. You see the same thing here, show router route table. So any OSPF length route in between CE1 and PE1 will be put into the routing table over any BGP length route. This is because OSPF has a lower preference than BGP. BGP's got a preference of 170, which is quite high. OSPF has got a preference of 10. This matters more on CE1. If you look on CE1, you'll see that the 150 network is being lent and it's been put into the routing table with a preference of 170. OSPF externally lent routes is got a preference of 150, which is still lower than BGP. And then you've got the remote OSPF, which is the 10. So this will always take precedence over any BGP length route. Currently, PE2 cannot ping any network in CE1, and likewise, CE1 cannot reach any network in PE2. This is because they both don't know about each other. The CE1 routes are OSPF routes, and we need to redistribute this into BGP to allow communication in between CE1 and PE1. Now, in the real life network, you might not need to do this. This is purely based on your design. If you need to do this, there's no need for CE1 to be redistributing its own local network outside. But we're just doing this for demonstration purpose. So let's go ahead and configure our task 7, which is to modify the existing policy on PE1 to include all the OSPF length routes within the AS1. This will allow both PE1 and CE1 to reach each other. So let's go to PE1 rather, and do this. Let's have a look at what we currently have in our policy again. Show router policy. And our policy is distribute loopback. So we only have one entry in this policy at the minute. So what we're going to do, we're going to add another entry which is going to start to redistribute all the OSPF length route into BGP. And to do that, we issue the configure router policy options, return, and then we begin with the begin keyword. So our policy statement is the distribute, the only one we have. It returned info. So we now want to enter a new entry, which will be entry 20. Entry 20. We now want to say to this policy that we want to redistribute anything that it learns from the protocol OSPF. So we're going to say from protocol, and our protocol is, if you tab here, will tell you, it will show you all the protocols that you can currently redistribute into another one. So this is the way you can do redistribution from one protocol to the other. But for now, all we want to do is redistribute OSPF into our BGP process. So our keyword again is going to be OSPF, and our action is going to be to accept it. Exit, exit. If we do info here, it will show us what we've just configured. So we now have two entries within our export policy, and those entries are, the first one, entry 10, says redistribute any locally connected network, which is our loopback interfaces, our connected interfaces. And the second entry is saying anything that it learned from OSPF, it should be redistributed into BGP. We now need to commit for this to take effect. It return exit all. Now let's go over to PE 2 and see what we now have within the routing table. This might take a while because BGP is quite slow. It's slower than OSPF. OSPF is quite very quick to converge. So let's wait a bit and then issue the show routing table again. Show router routing table. So what has changed? So if you can see, we had 6 routes previously. That was before we made a change to the export policy, and now we have 7 routes in our routing table. So this has included the routes from CE1, and I issued a ping previously to try and get to the system interface of CE1. I couldn't. Let's now test to see if now we can. So ping 140.10.0.12. Yes, we can. This is mainly because we are now redistributing OSPF into our BGP process, and now BGP is now aware of our OSPF network on CE1 and is then sending this information to PE2. PE2 now has the routes to get to CE1 within its routing table. Let's check the routing table before we go. We still have 7 routes. Let's go over to CE1 and do the same thing. When we checked the routing table earlier, we had 7 routes. What has changed? I don't think anything will have changed here, to be honest. But let's confirm anyway. Yes, so nothing has changed here. All we've done is we've told PE1 to redistribute all the OSPF routes into BGP, and that had taken effect on PE2, because previously PE2 does not know how to get to CE1. If we had not done that redistribution, there was no way for PE2 to know how to get to CE1. Let's now ping, to conclude, let's now ping the loopback interface on PE2, which is the 150.10.0.33. And now CE1 also now knows how to get outside of the ISP1 to ISP2. This has concluded our BGP configuration. I hope you find this useful, and thank you again for watching. If you've not subscribed, kindly do so. Thank you.